Hello, my name's Mike Sloan. I'm Director at Technical Composite Systems in Southwest UK, and I'd like to talk to you about our NATEP project, Composite Baseplates for Aerospace Antennas. Very successful project that finished a few months back. So over the next few slides, I'm going to talk about the challenges we were faced with and how we overcame them. A little bit of background, if I just start with the project partners, it was led by TCS, both technically and programmatically, and we were joined by some physicists at the University of Exeter and also antenna specialists at Cobham Aerospace Connectivity. Now, just to set the scene a little bit, I've borrowed a picture from the ATI here that really illustrates the challenges both in terms of complexity and criticality for aircraft being able to communicate. There's a lot going on. And there's a lot of hardware there, and we saw an opportunity to make it smaller, make it lighter, which benefits a number of users and installers. So here's a 787 just for balance, and you can see there's a vast number of antennas all put on the airframe after the fuselage has been built. They're all sticking out in the aerodynamic stream. And just looking along the sort of the dorsal of the fuselage, you can see a VHF blade antenna there and quite a bulky SATCOM antenna that sits proud. Now, one approach is to actually put these inside the aircraft, what's called a conformal antenna. So that was one approach that we chose, but that takes headspace within the aircraft. So if we can shrink the amount of volume that goes inside the aircraft, that is a big plus to the airline operators. So we attacked this with two approaches. The first was using composite materials to reduce some weight, and the second was using physics, what we call metamaterials, to reduce size. So I'll talk first about composites. Really, our first challenge was to replicate a 6000 series alloy with a composite material. So we're talking carbon fibres, maybe epoxy resins, pre-preg materials to give you an indication. We had to consider the mechanicals, the environmental, the temperature. Heat and water are a big enemy to composite materials, so we had to take those into consideration, and electrical performance, both desirable and undesirable. Now, a conformal antenna system would typically look something like this. So there we have a base plate, which is the tray, and a radome, which is the lid. It's a bit like a pie, I like to think of it. In terms of size, that is 300 millimeters, maybe 400 millimeters in diameter as a start, but our solution is entirely scalable. How we approached this from a composite point of view was we did a detailed map of the requirements for the antenna, both in terms of the masses, the temperature requirements, various geometries, and we did a literature review looking at what materials we could possibly use, what would hit the spec, both from a technical but also a commercial point of view. Are these cost effective? Are they readily available? From there, we went on and did what we call our ply layups. So where are we going to put the individual fibres, and did some basic structural calculations to make sure that we had the allowables in hand. And then TCS went on to do a full tooling design, test article manufacture, and then test, which was the fun bit. So if I focus on the lightning test, this was a worst case scenario for our project in that the radome had somehow failed, maybe through an impact, and we wanted to test what would happen to the new base plate, the new composite base plate, if that saw a lightning strike. Now in aircraft, they talk about lightning strike as zones, the worst being the nose and the tips of the wings, the tips of the tail. They're the zone 1s, you've got zone 1A, 1B, 1C. And then moving down in terms of severity, you've got zone 2. The purple area is the one of most interest to us, which is zone 2A. You've got a lot of real estate there in the fuselage. So if we can pass zone 2A, we've got a lot of space with which to put a potential antenna. We took a series of 8 test articles to an instrumented test house, and we tortured them for a day. It was a lot of fun. Here's one of the live lightning tests. You can see our base plate in the middle, mounted in that metallic square frame, with the lightning pickup point in the centre of the base plate. There's a short alarm just before the strike, and then it all happens very quickly. There we go, that is a zone 1C test. Energy impulse going through the centre of the base plate, radially out to the pickup points, and it survived with flying colours. And that is the typical current versus time curve of the energy that goes into one of these components during a test. It is very arduous, but we had a significant success rate in terms of a pass. There is one of our test articles that's passed. So the lightning was attached right in the centre of the base plate and forced to travel through the radially out to the edges, so forced to travel across and through the composite material. And we were extremely pleased with the low level of damage that we saw on that test article. Having passed the lightning strike, we then went on to do a series of tests, environmental and mechanical, based on DO160. So that's some cyclic mechanical testing, some humidity, some fluid susceptibility. All of those tests passed as well. So a massive result for our project in terms of getting through what was quite a nervous time in terms of lightning striker composites. That was the composite side of the project. Now I'm going to present a couple of slides on behalf of the physicists at the University of Exeter, and they were tasked with using some clever physics to shrink our housing and effectively use what's called a meta surface. And the conditions they were given with was to have a percentage bandwidth of 50% and a depth of no greater than the wavelength divided by 12. Now, not getting into too much detail here because it's not my field of expertise and also time constraints. Antennas radiate in different directions. You can improve its performance in terms of its efficiency if you place that antenna in front of a perfect electrical conductor. A metallic surface works fine. Now, if you space that by its wavelength divided by 4, you get an optimal result. An artificial magnetic conductor allows you to bring the antenna much, much closer to that boundary condition, that mirror. And that was our challenge. How did we do that? Two things. One was a frequency selective surface, which is a patterned copper grid that is made using standard PCB techniques. And then we combined that with what's called a magnetodielectric material that allows us to bring the antenna much, much closer. So we significantly reduce the depth of this antenna, which equates to the headspace inside the aircraft. Just coming on to the highlights of the project, well, it was great to bring a team of people together, physicists, materials engineers, antenna engineers that wouldn't usually work together, all working on novel science. That was really enjoyable. Passing the lightning test was a big relief, but because of the NATEP structure, it allowed us to pursue our challenges through protected activity, budgets, resources, Gantt charts, etc. Throughout the project, we documented everything that we did, so we've got a substantial library of information to move forward with. And generated some really interesting intellectual property as well. Challenges weren't anything out of the ordinary in terms of our project, keeping design activities on track and coordinating different teams going in different directions. Again, you've got production demand, so you've got to protect your resources from that and getting over unexpected bumps in the road. Standard stuff for a project. The benefits to us were progressing something from an idea through to something that works, a technology demonstrator. That was a significant boost. And applying our skills to a different technical arena. I've just talked about physics. I didn't know too much about that before we started the project. I'm somewhat the wiser now. A small SME demonstrating our technical capability in this kind of arena is a massive plus for TCS. And we couldn't have done that without the support from the NATEP technology managers. What's coming up next is we're going to further engage with end users to look at getting these further up the technology readiness level from, say, a TRL 7 right up through 8, 9 and beyond, to look at integrating these within specific applications, because we've done a technology demonstrator. It does need a specific requirement for us to tune the materials to suit. The NATEP program provided us with significant benefits, driven by the technology managers who provide support and guidance right from the very start of the application phases, right through to having regular quarterly meetings and ensuring that we meet our deliverables and our cost requirements. We couldn't have done that as an SME working with larger tier 1 companies and academic institutions without NATEP support, and I would place significant emphasis on the benefits of having a structured program from the very start. I would be very happy to talk to anyone that's interested in either of the technologies that we've developed. It's applicable beyond antennas as well. If you think there's a particular application, please don't hesitate to get in touch. We'd love to have a chat. Thanks for your time.